Hello, in this video we will generate the phi function over these values of x from negative 2.5 to positive 2.5, chart it, and regress it to the highest degree polynomial regression. We start with the phi function, which is RA formula, phi of the x values. Here you will find the polynomial regression to the sixth degree. Now we can use the same result, get the same result using norm test. So RA formula, norm test of the x values, where the mean is 0, standard deviation 1, and it's not cumulative, so it's 0. It is a probability distribution function. And we get the same, exact same results. We can also use this exponent function where we have RA formula, RA formula of the exponent of the x values. And we factor in the square. So it's to the power 2. And we factor in the negative 0.5. 0.5 times, and it's negative. Now we're closer. Next, we divide by square root of 2 pi. So this is divided by square root of, let's start with pi. We're almost there. Then multiply by 2. 2 times pi. Now we got the exact same results. We will expand this using the Taylor-Maclaurin series expansion, where it is equal to, phi is equal to the summation of a times x to the power of 2n, where the coefficient a is equal to negative 1 to the power n all over n factorial times 2 to the power n times the square root of 2 pi. And the values will range from 1 to infinity, the n values. So we start with the n values 0, 1, 2, 3, 4, but in this case we're limited to our dataset range, which is still good enough. Next, we will enter the expansion, which is RA formula, SERIESSUM. The x values will be here. So, and the n will be the power that is starting 2 to the n, so 2 to the 0. 2 to x to the 2 to the 0 is x to the 0. And then x to the 1, 2 times 1 is 2. So x to the 0, x to the 2, or x squared, x to the 4th, and x to the 6th. So we start with this x raised to the power, starting power is 0. But the interval of the power will be 0, 2, 4, 6, because 2 times 0 is 0, 2 times 1 is 2. So the interval will be 2. And the coefficient will be this range. So we're gradually getting there. We will now work on the coefficient, which is RA formula. Let's start with the numerator, negative 1 to the power n. Now that we have the numerator, then we work on the denominator, which is, there are 3 parts in the denominator. So we have 3 parts in there. So there are 3 parts. So the first part will be factorial. Factorial of n. So the first part. Next, we work on the second part. So we work on the second part times 2 to the power n to the power n. Okay, we're getting there. The third part, this is square root 2 pi times square root of, let's work on pi first. We're getting there. We add 2 times pi. Finally, we found it, we got it. Now let's look at the regression coefficients. They're the same for B1, B0, they're the same, 0.396. B1, they're all 0. B2 is 0.813, 0.183, negative 0.183. B3 is 0. B4, 0.0321, so on. Our A0 is 0.398. This is 0.396. Our A1 is negative 0.199. No, this is negative 0.183. So, but they're close. Our B2, 0.0498. It's very far away, 0.0331. We'll calculate this regression coefficients using LINEST. To do that, we will begin with the 1 comma x matrix. So we start with transposing these values. So we have this column will be x to the 0, this column will be x to the 1, this column will be x to x squared, x cubed, and so on, up to x to the 6. Start with x to the 0 column or the 1 column. So RA formula of the x values to the power 0. So that's our 1 column. We lock the reference so it does not move as we drag, copy to the rest of the 1 comma x matrix. So we drag this. This will be the x column, which matches to our x values. This will be the x squared column, x cubed column, and so on. Now that we have the 1 comma x matrix, we can now calculate the LINEST. LINEST of data y for the first part, the v function, and data x. Something's wrong because this should be data y. And for the second part is the red one, which is the exponent. So RA formula, LINEST again. We use LINEST. Data y and data x. And the expansion, the Taylor-Maclaurin series expansion. Again, LINEST, data y, and data x. Let's compare. Our B0, they're the same, 0.396. Our B1, they're all 0. Our B2, negative 0.183, they're also the same. B1 here is 0.398, this one is negative 0.199, so almost close. So that's a B1. Our B3, they're all the same, 0. B4, they're the same, except for this one. This is an expansion, it's an approximation, limited by the range, the range from 0 to 10 only. So it's not accurate. B5, they're all 0, and B6, they're all the same. So, except for this one, but it's a very small error. This completes the Google Sheets fee function expansion, and LINEST polynomial regression.